crop circles that we're aware of in the modern era.
The greatest mystery of crop circles does not lie in their massive patterns, but is hidden within the wheat stalks themselves. When Google's AI analyzed 12,000 data records over a span of 50 years, it uncovered a paradox. In the most complex formations, the wheat is not crushed or broken, as it would be under wooden planks. Instead, the nodes bend on their own, and the stalk walls rupture with micro holes torn from the inside out. Physical evidence that the internal moisture was flash heated to the point of boiling. Crude mechanical force cannot boil plant cells. So what kind of physical mechanism could deliver such rapid heat at the microscopic level, while preserving large-scale geometric perfection without burning the plants? The 1991 smokescreen, the confession that froze science. The crop circle phenomenon began capturing the attention of the entire world toward the end of the 1970s in the Wiltshire region of southern England. At first, they appeared as simple circles, but by the 1980s, they rapidly evolved into ever more complex geometric designs, igniting countless theories. The debate reached its climax in 1991 when everything seemed to end with one television broadcast. Two elderly men, Doug Bauer and Dave Chorley, publicly confessed that they were responsible for hundreds of these circles as an elaborate prank spanning more than a decade. With just a few wooden planks, some lengths of rope and a cap serving as a sighting tool, they recreated their technique right before the cameras. That performance delivered an enormous sense of psychological relief. More importantly, it established a single and definitive physical rule for the whole phenomenon: mechanical crushing. From a physics standpoint, the principle of the wooden plank is remarkably simple and undeniable. When a crude mechanical force, specifically the full weight of an adult man bearing down on a plank of plywood, presses upon a hollow and brittle wheat stalk, the biological outcome is unmistakable. The tough cellulose wall of the stem is crushed instantly. The stalk cannot bend gracefully. Instead, it snaps sharply, creating jagged fractures at the point of pressure. The aftermath of this breakage is lethal. The vascular bundles within the core that transport sap are completely severed, cutting off the flow of water and nutrients. The inevitable result is that the upper portion of the plant dies yellow and withers away within just a few days. These are the clear physical signatures of brute muscular force, obvious and impossible to counterfeit. This explanation proved so perfect that it became an enormous cognitive bias. Both the media and academic scientific institutions adopted it as the only lens through which to interpret the entire phenomenon. Every design in the fields was automatically presumed to be the work of plank-wielding vandals. The story served as a self-censoring mechanism that stifled any calls for serious scientific investigation for the following 30 years. This explanation was so flawless that it possessed only one single weakness. It only held true when observed from afar. So how would this veil of history be dramatically torn apart when botanists chose to collect wheat stalks from the centers of the most intricate patterns and examine them under the cold illumination of the electron microscope? Microscopic examination, the joints that cannot be broken. Google's artificial intelligence uncovered a long overlooked truth when it performed cross-analysis between macro-scale images and plant physiological data. In the most complex crop circle formations, the cellular structure stood in complete contradiction to the laws of mechanical force. Wheat stalks gathered from these areas revealed that the growth nodes known as pulvini showed no signs of crushing or snapping. Normally, the crude mechanical force from a wooden plank would fracture or pulverize these nodes due to the dry and brittle nature of mature wheat. Yet the biological data recorded that these growth nodes had swollen and bent in smooth curves. Their length had increased from 115% to more than 200% compared to neighboring upright plants. Physically speaking, plant cells can only stretch and bend smoothly when the cellulose fibers are softened by high temperatures. This process resembles heating a rigid plastic tube until it becomes pliable and slumps under its own weight. Once the heat source is removed, the structure hardens in its new position while the outer surface remains intact. The artificial intelligence flagged a critical anomaly here. The wheat remained alive. If subjected to ordinary fire or flames, the plant tissue would die, and the exterior would show scorching. However, field reports confirmed that the epidermis of the wheat showed no traces of smoke or charring. The sap channels inside the stem core continued to function smoothly. These flattened wheat plants kept performing photosynthesis, drawing water and nourishing their grains right up until harvest time. Human muscular force applied through a plank can only produce mechanical crushing and breakage. It cannot stretch plant cellular tissue while keeping the plants alive. Google's artificial intelligence algorithm confirmed that this particular group of crop circles required an extremely sophisticated thermal intervention mechanism, one that acted directly on the cellular structure rather than relying on simple physical pressure. What mechanism could boil the water inside wheat stalks so rapidly that it would tear cell walls from the inside outward without leaving any scorching or smoke marks on the outer surface? Expulsion cavities, traces of a giant microwave oven. The intensity of that invisible heat did more than just soften the plant exteriors. Upon deeper analysis of the cellular core structure, the artificial intelligence exposed a distinctive microscopic signature of violent force, the phenomenon known as expulsion cavities. These are tiny perforations that appear along the stems at the joints. Yet the true anomaly lies in the mechanical direction of the tears. The cell wall edges are ripped apart from the core outward. According to the laws of thermodynamics, the only physical mechanism in the world capable of producing this type of internal to external cell wall tearing is flash boiling. Wheat stalks always contain a natural level of internal moisture within the core. When this water is suddenly heated to boiling point in just a fraction of a second, it turns to vapor and undergoes a sudden volume expansion. This expansion happens so rapidly that it generates an enormous pressure buildup within the confined space of the cell walls. With no immediate escape route, this pressure bursts through the plant tissues to release energy into the environment.